Welcome back to the deep dive. So today we're taking on a concept that's, well, it's absolutely fundamental to computer science.
Right.
But for so many programmers, it's this huge intellectual roadblock. We are diving deep into the world of pointers. You've come to us with some pretty technical notes, I see, covering core computing architecture and memory manipulation. And the goal is to really master this idea, right? Variables that don't store data, but instead they store location.
It really is the ultimate shortcut to understanding system architecture. Pointers are, they're the bridge between the clean, high-level code you write and the messy physical reality of the machine.
Okay.
To really get this, you have to shift your perspective a bit. As a programmer, you use identifiers, those nice human-readable names like age or total score.
Sure.
But the central processing unit, the CPU, it doesn't know what a score is. It only sees physical memory addresses.
So we have two different languages operating at the same time, and our job today is to, learn the CPU's language.
Precisely. Pointers are the variable type designed specifically to store and manipulate those numerical memory addresses. They put you, the programmer, directly in charge of the computer's geography.
Okay, let's unpack that then. Let's start with the basic geography of the computer. Random access memory, RAM. We all know it's fast, temporary storage, but why is it so essential here?
Because nothing happens outside of RAM. A running program is a chunk of RAM, and all the data that program uses, it must also be loaded right there.
Right.
You can think of RAM as, a gigantic, organized city block made up of individual mailboxes.
Okay.
Each mailbox is a byte of memory, and every single one of those mailboxes has its own unique numerical address.
That's a great analogy. So when I declare a regular variable, say int x equals 10, I'm not just creating a value.
No, not at all.
I'm asking the system to find an empty mailbox, a location, and write the value 10 inside it, and then assign the label x to that specific mailbox address.
That's the key mapping. That's it, exactly. Variables are just programmer-controlled identifiers that map directly to a memory location. Every piece of data, even that literal value 10, lives somewhere specific in memory.
And that brings us to our guest of honor then, the pointer. If variables are these convenient labels for values, what exactly is a pointer?
A pointer is a special type of variable that only stores a mailbox address.
Only the address.
It doesn't care what value is in the mailbox. It only holds the number of the mailbox itself. So if a regular variable represents the content, a pointer represents the map coordinate.
I see.
They're indispensable for advanced memory handling. And just like any variable, you have to declare a pointer before you can use it. You have to specify what type of data it's expected to point to.
That makes sense. We're telling the compiler, hey, this variable is going to hold an address, and at that address, you'll find an integer or a string or whatever it is.
That's right. And this is where the immense power of, low-level languages really comes in, because pointers let you directly manipulate memory.
Which is the foundation of efficiency and control.
Exactly.
And that control, it starts with two tiny but mighty symbols, right?
Yeah.
The addressive operator and the dereference operator. Let's start with the address part. How do we get the address of a regular variable?
We use the ampersand and RIC. This is the addressive operator. So if you have that regular variable, let's go back to x holding the value 10.
Okay.
If you write an x, the computer doesn't give you 10. It gives you back this huge numerical address, like 0 by 7, free 6, A8, B794, where that value is physically stored in RAM. You use the ampersand to load a pointer variable with the address of a regular variable.
So the ampersand is like asking the mail carrier, what is the street address for the person named X?
Precisely. And that an operator, it has another incredibly important use beyond just loading pointers. It's the whole mechanism for pass-by reference in functions.
Pass by reference. So instead of sending a copy, you're sending the address.
You're sending the address of the data, not a complete copy of the data itself.
And why is avoiding that copy such a practical choice? Why not just pass the whole variable?
It's efficiency. Just pure efficiency. Imagine you have a variable that represents a massive data structure, say a high-resolution image file that's 50 megabytes.
Right, something huge.
Or a complex array with thousands of entries. If you pass that variable to a function by value, the system has to take all 50 megabytes and copy it entirely into a new location just for the function to use.
Which takes time and memory.
A lot of time in memory. But if you pass it by address using the operator, you only pass a tiny address, maybe 8 bytes long. The function can then work directly on the original 50 megabyte structure without any copying overhead.
That's a huge performance gain, especially on constrained systems. Okay, so if the ampersand lets us get the address, we need the reverse. Once we have an address stored in a pointer, how do we access the value sitting at that location?
That is the role of the asterisk.
Yeah.
This is the dereference operator. When you use the asterisk in front of a pointer variable, you are telling the CPU, follow the address stored inside this pointer and retrieve the data that's sitting at that location. It's what turns the map coordinate back into the actual content.
So the asterisk really has a dual life here, and I think this often confuses learners.
It absolutely does. When you declare a pointer, say int my pointer, you use the asterisk to signify its type. Here it means this variable is a pointer to an integer.
Right.
But when you use that pointer later, like my pointer, it's 20, it means go to the address inside this pointer and change the value there to 20.
So it's all about context.
The distinction is critical.
Yeah.
Are you talking about the container, which is a pointer variable, or the content, the value it points to?
That clarity is essential. Once you get those two operators for the address and for the value at the address, you've really unlocked the core system.
You have.
And that brings us to where the true power and maybe the terrifying peril resides, pointer arithmetic.
It's where the low-level nature really shines. You can perform arithmetic operations on memory addresses just like they were normal numbers. You can add or subtract integers from a pointer, and that causes it to move through memory.
Okay, now this is where we need total clarity for you listening. If I have a pointer p pointing to an integer, and I write p plus 1, I'm not asking the pointer to move just one single memory byte over, am I?
No.
Because if an integer takes up 4 bytes, moving 1 byte would land me right in the middle of it.
And that's the genius of it. You've hit on the key conceptual detail our sources emphasize. Pointer arithmetic is scaled. The compiler is smart enough to know what the pointer is pointing to. So if your pointer points to an integer that occupies 4 bytes, when you add the number 1, the system automatically calculates move the address forward by 1 integer's worth of space.
So adding 1 actually moves the pointer address 4 bytes forward. It moves it to the next available valid integer location. It's moving by data type blocks.
Exactly. This makes traversing sequences of data, like arrays, incredibly efficient. You can just step from element to element by incrementing the pointer by 1.
Now, here's where this immense power, well, it turns into a liability. Our sources flag this ability to move the pointer around as potentially dangerous from a security point of view. How does that happen? How does this low-level control turn into a security risk?
It's the direct path to one of the most common and critical software vulnerabilities.
Buffer overflow.
Buffer overflows. A pointer is designed to point to a valid block of memory. But what if you use pointer arithmetic, or more commonly, what if a malicious user inputs way too much data into a buffer, say a password field, and that input causes a pointer to walk right past the end of its reserved memory block?
It overflows the container.
It overflows. And because the pointer can now reach arbitrary memory locations, it might start overwriting data, or even worse, overwriting function pointers or return addresses stored elsewhere on the stack.
Oh, wow.
And an attacker can potentially redirect the flow of the program by replacing that legitimate address with the address of their own malicious code.
So a basic error of forgetting to bounds check user input or just mismanaging pointer arithmetic could be the starting point for a major system-wide security flaw.
Absolutely. It's why these basic concepts are so vital. Pointers must point to valid, useful addresses. Uninitialized pointers, or pointers that have been moved past the end of an array, are invalid.
And the scary part is, the compiler won't complain when you declare them.
Not at all. The error happens much later, at runtime, when you try to dereference it.
And dereferencing an invalid pointer might crash the program, or it might just give you garbage data, which is sometimes even harder to debug.
The unpredictability is the risk. It highlights the direct link between precision in pointer handling and the overall stability and security of the application.
That provides a necessary dose of gravity. We've seen the danger, but that danger comes with immense power, especially when we talk about creating memory on the fly dynamic memory allocation. Up until now, we've talked about variables whose memory needs are known at compile time.
That's memory the system knows it needs before the program even runs. But modern programs are flexible. They often need memory that's determined only during runtime while the program is actually executing.
Give us a concrete scenario.
Sure. Imagine a database program that asks the user, how many customer records do you want to input today? You have no idea what that number will be when you compile the program.
It could be 5, it could be 5 million.
Exactly. In such cases, the program needs to dynamically request memory only when the user inputs that number.
And this requires us to look at the two primary divisions of system memory, the stack and the heap.
The stack is where memory for regular local variables, your auto variables, is allocated. Think of the stack as a fast food counter. Orders are quick, small, placed one on top of the other, and automatically cleaned up when the function is done.
And its size is determined at compile time.
Right. And the heap. The heap
Yeah.
segment is the storage facility. It's much larger, more flexible, and memory is allocated here only when requested dynamically during runtime.
And this is where pointers become essential, used alongside the keywords new and delete.
That's it.
New is what we use to ask the system, give me a block of memory for these 5,000 customer records on the heap. And new returns a pointer to the very beginning of that new block.
Exactly. The pointer holds the address of that block, so you can access it. But here comes the responsibility. The crucial management step that honestly differentiates great programmers from good ones.
The memory leak?
The memory leak. Unlike stack memory, which cleans itself up automatically like a fast food cleanup crew, dynamic memory on the heap is manual. If you allocate memory with new, you must explicitly call the delete keyword when you are finished.
And if you forget?
If you forget to call delete, that memory is essentially trapped. The system thinks it's still reserved by your program, but the program can't access it anymore. It's lost space.
That sounds like a fatal problem, especially for long-running applications.
It is. Imagine a web server running for weeks, allocating a small block of data for every new client connection and failing to deallocate it.
Yeah.
Even if it's only 5 kilobytes a minute over a few days, that adds up to gigabytes of trapped memory. The system slowly starves of resources, leading to a performance bottleneck or eventually a crash. The contract of using pointers for dynamic allocation is manual accountability.
That really underscores the gravity of memory management. It's not just some technical footnote. It's a major operational issue.
It's crucial.
Let's shift gears now to how pointers facilitate communication between different parts of the code pointers in functions. We talked about pass by reference being efficient, but what happens when a function receives that address?
Well, if a function receives a pointer as an input variable, what we call the formal parameter, it is given the power to alter the original data. If the function changes the value pointed to by the parameter, the original variable, the actual parameter, changes as well.
That's the whole point, right? To modify external data efficiently.
Right. But this is also where unintended side effects can creep in. If I pass a pointer to a function just hoping it only reads the data, say, to calculate an average score, and it accidentally modifies one of the scores, that's a nightmare bug.
So how do we prevent that?
The standard critical practice is to pass those pointers as constants. Declaring a pointer parameter as constant essentially makes it read only within the function's scope.
Oh, okay.
You can still use the pointer to access the data quickly, but the compiler will stop you from changing the value it points to, which mitigates the risk.
Security and safety through syntactic rules.
Well,
Okay, let's close with one final advanced application that truly shows the versatility of addresses. Pointers to functions.
we spent this entire time talking about pointers storing the address of data variables.
Right.
But functions themselves are code, and code must live in memory. So functions also have addresses. A function pointer is just a variable designed to store the address of a function.
And what's the practical application of that? Why would I ever want to point to a function?
It allows for truly flexible, dynamic code. The most common use is for callback mechanisms. You might call a system function, say, a function to store a massive list of objects, and that function needs to know how to compare those objects.
Okay.
Instead of hard-coding the comparison logic, the system function asks you to pass in a function pointer, telling it, here is the address of the custom comparison logic you should use.
So this is how powerful system libraries and APIs let you customize behavior without rewriting their core code. You're just handing over control flow. The syntax for declaring this is a bit thorny, though, isn't it?
It requires parentheses around the function pointer name to avoid ambiguity, but the concept is simple. You're treating code itself as data that can be passed around. It speaks to the core identity of the pointer. Anything that lives in memory data, structure, or code has an address, and anything with an address can be pointed to.
That is a phenomenal summary of our deep dive. We started with the foundational geography of RAM, realizing variables are just user-friendly labels for memory addresses. We mastered the power and the peril of the address of operator and the dereference operator. We navigated the treacherous landscape of dynamic allocation, understanding the critical difference between the automated cleanup of the stack and the manual responsibility of managing the heap with new and delete to prevent memory leaks.
Right.
And finally, we saw the advanced utility of passing pointers to functions as constants, and even using function pointers to pass around executable code.
You now have the full conceptual framework you need to move into real application. You'll see these concepts immediately, for example, in the provided exercises which require using pointers and dynamic memory to manage data to calculate, say, the area and perimeter of a rectangle. The theory is now ready for practice.
And here's where it gets really interesting as you apply this knowledge. We have high-level programming languages today like Python, Java, or C# that are designed specifically to hide pointers and perform automatic memory management. They essentially shield a programmer from the dangers of the heap and pointer arithmetic. So given that low-level pointer management is the root of so many catastrophic software bugs and security flaws, are these managed pointerless languages a necessary evolutionary step towards safer software? Or are we sacrificing critical low-level control and performance just to avoid the complexity? That's something for you to mull over as you start applying this knowledge.